Hey, you. Yeah, you with the beautiful brain. Ever tried to picture something that just doesn't end?
Like, really sit with that for a second.
Does your mental screen just sort of flicker and die? Do you get this vague sense of, well, just more? And here's the kicker. Could there be different kinds of more that never end? We're about to dive headfirst into this delicious abyss because that's exactly what The Infinite book by John D. Barrow dares to do.
It's a real roller coaster of thought, isn't it? Zooming through mathematics, cosmology, philosophy.
Even those moments when you're just trying to count all the crumbs on your kitchen counter, all seen through this, well, bonkers lens of infinity.
And trust us, this isn't some dry academic lecture.
No way.
Think of it more like your personal VIP tour through the most bewildering, maybe awe-inspiring ideas humanity has ever cooked up.
We're talking paradoxes that'll tie your neurons in delightful knots.
Yeah, those are fun.
And the genuinely universe-altering implications of what never-ending might actually mean.
It gets pretty deep.
So if you're ready to have your perception of, well, everything stretched further than that time I tried to wear jeans 3 sizes too small, then stick with us. We promise to make it fun, keep it clear, and by the end, you'll be the coolest conversationalist at your next gathering.
Maybe?
And hey, if your mind feels suitably expanded and you want more trips to the edge of understanding, why not tap that like button and subscribe?
Consider it your cosmic thank you note.
All right, let's unpack this infinite onion, shall we?
Let's do it. Barrow starts by grounding us, in the intimations of the infinite that we encounter in our daily lives.
Intimations, I like that word.
Yeah. Like, think about looking up at a clear night sky. That feeling of endlessness as your gaze just stretches out into the cosmos.
Yeah, it's like your eyeballs are trying to reach a horizon that just isn't there.
Exactly.
Or even simpler, just try counting. You get to 1 million, 1 billion, a gazillion.
Yeah.
And you just know you could keep going, right?
Yeah, there's no final number hiding behind some cosmic curtain.
And Barrow points out that the very way we write numbers, especially with our, elegant Indo-Arabic system and that humble zero.
That zero is key.
It makes it so easy to represent numbers getting bigger and bigger without limit. It's almost built into our mental software.
But, and this is important, Barrow gently reminds us that that feeling of endlessness isn't quite the same as the rigorous mathematical concept of infinity.
Right, there's a difference.
So to get there, he starts exploring the idea of subdivision, the seemingly endless possibility of cutting something into smaller and smaller pieces.
It's like a loaf of bread. You can slice it, then slice those slices.
And imagine doing that forever.
Right. You picture these infinitely tiny crumbs, smaller than atoms, smaller than anything we can really conceive.
But here's where reality gives us a little nudge, as Barrow puts it. In the real world, we hit a limit. We get down to molecules, then atoms, then subatomic particles. There's a bottom floor, eventually.
Even if we haven't fully mapped it yet. It's almost like William Blake was hinting at this when he wrote, "To see a world in a grain of sand."
Exactly. He's finding the profound, maybe even the seemingly infinite, within something finite.
It's that contrast between our abstract ability to imagine endless division and the concrete limits of the physical world.
Precisely. Barrow then pivots to what he calls geometric infinities. Picture drawing shapes on a piece of paper, a triangle, a square, a pentagon.
Okay.
You can imagine adding more and more sides, getting closer and closer to a perfect circle. It feels like an infinite playground of polygons.
It does, like this two-dimensional universe where you can just keep morphing shapes forever.
But then, bam, Barrow hits us with a curveball. When you jump up to 3 dimensions and think about regular solid shapes, the platonic solids, like cubes, pyramids, octahedrons.
The fancy dice shapes.
Right. Suddenly, the number of possibilities becomes incredibly limited. There are only 5.
Only 5. Wait, how does that work? More space, fewer shapes.
Exactly. Think about it. In this seemingly more spacious realm, the rules become stricter. It's weird, isn't it? Having more dimensions can actually impose more constraints.
That is properly weird.
It's a fantastic early example of how our intuitions, built on simpler scenarios, don't always hold up when we venture into more abstract or higher dimensional realms.
Okay, I see.
And this sets the stage for Barrow to revisit Zeno's paradoxes of motion. Those ancient brain ticklers that first really wrestled with the infinite divisibility of space and time.
Ah, Zeno, the master of the philosophical head fake. We're talking about Achilles and the tortoises and the arrow that's always still, right?
That's them.
For anyone who hasn't had their brain pleasantly scrambled by these, what's the core conundrum?
Okay, picture this. Achilles, the fastest runner, is in a race against a tortoise who gets a head start.
Got it. speedy guy, slowpoke.
Zeno argued that Achilles can never overtake the tortoise because every time Achilles reaches the tortoise's previous position, the tortoise has moved a little bit further ahead. This process of catching up, closing the gap, theoretically goes on forever.
Infinitely smaller gaps.
Right. And the arrow paradox is similar. Zeno said that at any single instant, an arrow in flight is motionless. If time is made up of these frozen instants, then the arrow never actually moves.
It's logically infuriating. Your eyes tell you the arrow's flying, but Zeno's logic ties your brain in knots. So how do we escape this philosophical trap? Barrow touches on the modern understanding, doesn't he?
Precisely. Modern mathematics gives us the concept of limits.
Limits.
Like in calculus.
Yeah. We can actually sum up those infinite series of ever smaller distances and time intervals and arrive at a finite total. Achilles does overtake the tortoise.
Phew. Okay, good.
And in the physical world, as Barrow points out, the finite speed of light and perhaps even the granular nature of space-time at the smallest scales suggests that we can't just keep dividing space and time infinitely in a physically meaningful way. Okay, so our everyday intuition, backed up by some clever math and physics, helps us escape Zeno's logical labyrinth. Now, Barrow starts to categorize the infinite into actual, fictitious, and factual. Break that down for us. What's the difference?
This is where Barrow delves into humanity's long and winding relationship with the concept of infinity, often intertwined with our deepest philosophical and theological ponderings.
Okay.
He highlights Aristotle's foundational distinction between potential infinity and actual infinity.
Aristotle, always laying down the groundwork.
Yeah.
What was his take on these two flavors of forever?
Aristotle essentially said that only potential infinity exists.
Potential infinity.
Yeah. Things can potentially go on without, like our counting example, but an actual completed infinity, like an infinite number that's somehow finished, he thought was a no-go.
Why not?
Well, he worried that if actual infinity existed, it would undermine our ability to understand anything. I mean, how can you fully grasp something that is, by definition, limitless?
So for Aristotle, the universe itself had to be finite, even if it was surrounded by an infinite void of nothingness. It's all about the idea that things need boundaries to be comprehensible.
Exactly. Then Barrow moves into theological perspectives, and this is where it gets fascinating.
Religion and infinity.
Yeah, the idea of infinity has been central to many religions, particularly when trying to describe the nature of God. It's this constant push and pull between the infinite attributes ascribed to the divine and the finite capacity of the human mind to understand them.
It makes sense. If you're talking about a being that's all-powerful, all-knowing, eternal, infinity seems like a necessary ingredient. But how do you even begin to picture that in your head?
Barrow brings in Pascal's brilliant concept of the double infinity, the infinitely large and the infinitely small.
Double infinity.
Pascal argued that we're constantly encountering these infinities in the world around us, from the vastness of space to the infinitesimal nature of matter, but our human reason can't fully grasp either extreme.
We're stuck in the middle.
Kind of. Yet he believed the undeniable infinity of numbers is itself an argument for knowing that infinity exists, even if we can't fully comprehend its essence.
So we know of it, but don't know it.
Pretty much. He even touches on Pascal's wager, that famous gamble where the potential infinite reward of believing in God outweighs the finite risk of being wrong.
Right, that ultimate high-stakes bet. It's certainly a unique way to think about infinity.
Mm-hmm.
What about Kant? Where did his famously nuanced mind land on all this?
Kant, as Barrow explains, saw the universe as potentially infinite in its extent and in the sheer number of possibilities it held, viewing this grandeur as a reflection of the divine. However, being Kant, he stressed the inherent limits of human understanding.
The limits. Always the limits with Kant.
He believed our minds come preloaded with certain categories of thought. Think of them as mental filters.
Like pigeonholes for reality.
Sort of, yeah. And they inevitably shape how we perceive and process information about the world. So even if the universe is truly infinite, our experience and understanding of it will always be filtered through these finite mental frameworks.
So even staring out at an infinite cosmos, our brains are still running on limited software. It's a sobering thought.
It is.
Okay, so from grand philosophical and theological musings, Barrow then plunges us into the madness of mathematicians and a hotel.
Yes.
This sounds like where the concept of infinity starts to get truly mind-bending and delightfully counterintuitive.
Absolutely. This chapter is a fantastic showcase of how mathematicians have wrestled with the actual concept of infinity as a concrete entity, leading to some results that feel like they've been beamed in from another dimension.
Bring it on.
It all kicks off with Hilbert's Infinite Hotel.
Oh, this is a classic. For anyone who hasn't had the pleasure, paint us a picture of this infinitely accommodating establishment.
Okay, imagine a hotel with an infinite number of rooms. Room 1, room 2, room 3, forever.
Infinite rooms, got it.
And every single room is occupied, not a single vacancy. Full house.
Infinitely full. Okay.
Now, a new guest walks in, looking for a bed. Can the hotel manager find a space for them?
Intuitively. No, it's full.
Incredibly, yes. The manager simply tells the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Shifting everyone down one room.
Shuffling the infinite line.
And boom. This instantly frees up room 1 for the new arrival.
It's that cosmic reshuffling that makes your brain do a little hiccup. Even when it's full in the most complete way imaginable, you can always make room for one more.
But it gets even crazier, right?
Oh, I bet it does. What if an infinite bustle of new guests pulls up?
Exactly. You'd think an infinitely full hotel couldn't possibly accommodate another infinite set of guests.
Seems impossible.
But the ingenious manager has another trick up his sleeve. He tells the guest in room 1 to move to room 2.
Okay.
The guest in room 2 to room 4, the guest in room 3 to room 6 generally, the guest in room Marion moves to room 2 it.
Doubling all the room numbers.
Right. This leaves all the odd-numbered rooms vacant, and since there are infinitely many odd numbers...
The infinite busload of new guests can check right in.
Wow. It's this concrete demonstration of how infinite sets behave in utterly bizarre ways compared to our finite experiences.
It really is. Barrow then brings in Albert of Saxony's paradox, which highlights similar strange properties.
Albert showed that if you have an infinitely long beam of wood, you can theoretically cut it into an infinite number of cubes.
Okay, infinite beam, infinite cubes. Seems reasonable so far.
And here's the mind blower. The number of these cubes can be shown to be more than the original beam in a specific mathematical sense.
More cubes than beam. How?
It led to the formal definition of an infinite set as one that can be put into a one-to-one correspondence with a proper subset of itself.
A subset, like part of the original group.
Exactly. Think back to the hotel. The set of all guests after the new arrivals can be perfectly paired with the set of guests who were there before a subset of the new, larger group.
It's like getting infinite bonus content from something that was already infinitely packed. Then there's Galileo's paradox of squares and whole numbers. This one always makes me tilt my head and squint a little.
Galileo observed that for every whole number, 1, 2, 3, you can find a corresponding square number, 1, 4, 9.
Right.
Both sets extend infinitely, but intuitively it feels like there should be way more whole numbers because they include all those numbers that aren't squares.
Exactly. The squares feel like a tiny scattered selection from the vast landscape of whole numbers, like where's 2, 3, 5, 6, 7, 8.
But Galileo, in a stroke of brilliance, realized that the usual notions of greater, less, or equal just don't apply to infinite quantities in the same way we understand them with finite numbers.
So comparing infinities is tricky.
Very. Barrow clarifies this using the idea of one-to-one correspondence. You compare each whole number with a unique square number, 1 with 1, 2 with 4, 3 with 9, and so on forever.
Ah, the perfect matching again.
This perfect pairing shows that, in terms of how many there are, the cardinality, these two infinite sets are actually the same size.
Okay, so it's about this perfect matching, this infinite dance between the elements of two seemingly different infinite sets. Now, up to this point, we've been talking about countable infinities, things you can, at least in theory, list out, even if the list never ends.
Right, like the whole numbers, the even numbers, the squares.
But then Georg Cantor strides onto the scene and blows everything wide open with the concept of uncountable infinity.
Yes, Cantor's work was revolutionary, absolutely game-changing. He proved that there are indeed infinities that are fundamentally bigger than the infinity of natural numbers.
Bigger infinities.
Yeah.
Okay, my brain is starting to stretch again.
His first big surprise was showing that even the rational numbers, all those fractions you can imagine squeezed between any two whole numbers.
Like 12, 13, 23, 14, 34. Infinite possibilities.
They're also countably infinite. He used this incredibly clever diagonal method to prove it.
Wait a minute. All those infinite fractions, all those possibilities between 0 and 1 and between 1 and 2, they're still just as numerous as the regular old counting numbers. That feels deeply wrong.
And does. It assaults our intuition. But Cantor devised a systematic way of listing all possible fractions, ensuring that no fraction is missed in his infinite list.
A way to count the fractions.
Essentially, yes. The shocker is that what feels like a vastly denser set is actually the same size of infinity as the natural numbers. Called it Aleph Naught. But then came his truly earth-shattering result. His proof that the real numbers, all those decimals, including those never-ending, non-repeating irrational numbers like pi or the square root of 2.
The ones you can't write as simple fractions.
Exactly. Those are uncountably infinite.
Okay, this is where infinity goes from being really big to being a whole other level of big. How did he even begin to prove something like that?
He used another ingenious diagonal argument, but this time with decimals.
Another diagonal trick.
Yep.
He imagined a hypothetical list of absolutely all real numbers between, say, 0 and 1. Just assume you could list them.
Okay, a supposedly complete infinite list.
Then, he constructed a brand new real number. He looked at the first decimal place of the first number on the list and changed it. If it was a 3, he'd make it a 4, for example.
Huh.
Then looked at the second decimal place of the second number and changed that, and so on, down the diagonal of this infinite list.
Creating a new number by changing each digit on the diagonal.
Precisely. This newly constructed number, by its very design, cannot be anywhere on the original supposedly complete list because it differs from every single number on that list in at least one decimal place.
Because it's different from number 1 in the first place, different from number 2 in the second place. Clever.
Exactly. This proves that no such complete list is possible. The set of real numbers is fundamentally larger than the set of natural numbers. It's an infinity that you simply cannot count, a bigger infinity.
Wow.
So there isn't just one flavor of forever. There's a whole infinite menu of them, with some infinities being astronomically bigger than others.
That's the mind-blowing takeaway. Barrow then talks about the power set as another way to climb this ladder of infinities.
The power set, what's that?
For any set you can imagine, finite or infinite, the power set is the set of all its possible subsets, all the different combinations of elements you can make from it.
Okay.
Cantor proved that the power set of any set is always strictly larger than the original set. So if you take the infinite set of natural numbers, its power set represents an even larger infinity. And the power set of that set is larger still.
Generating an endless, ever-ascending hierarchy of infinities. Just, wow.
It's incredible. But this groundbreaking work wasn't exactly met with a ticker tape parade, was it? Barrow describes it as a mathematical civil war.
Oh yeah, with Cantor facing some serious pushback, especially from mathematicians like Kronecker. What was their issue with Cantor's infinities?
Kronecker was a staunch finitist. He believed that mathematics should only concern itself with things that can be constructed in a finite number of steps, starting with the natural numbers.
Only the countable stuff.
Pretty much. He viewed Cantor's actual infinities as meaningless abstractions, as dealing with things that don't truly exist in a constructive mathematical sense. He famously quipped, "God created the natural numbers, and all the rest is the work of man."
Wow, that's a pretty fundamental disagreement.
Yeah.
And even the legendary Gauss was skeptical of the idea of actual infinities, right?
Yes. Gauss, one of the giants of mathematics, saw infinity as more of a façon de parler, a convenient way of talking about limits and processes that go on without end rather than a completed actual entity.
So more of a useful shorthand than a real thing.
For him, yes. This prevailing conservative view in the mathematical establishment led to Cantor facing significant professional persecution. Kronecker actively blocked his attempts to secure a professorship in Berlin, and his work was often dismissed as nonsensical, even dangerous.
That's heartbreaking. To have such revolutionary ideas met with such hostility and misunderstanding, it apparently took a real toll on him.
It did, sadly. Barrow even mentions Cantor's own theological interpretations of his work.
Right. He saw a connection to God.
Yes, Cantor, who was deeply religious, saw his hierarchy of infinities as reflecting the perfection and boundless nature of God. He believed that God had instilled the concept of both finite and infinite numbers in the human mind as a reflection of his own divine attributes.
A fascinating and poignant intersection of cutting-edge mathematics and deep spiritual beliefs.
Absolutely.
Okay, so mathematicians have this intricate and often mind-bending understanding of infinity full of different sizes and strange behaviors. But what about physicists? Barrow then takes us into the realm of physical infinities. Are they as comfortable with the infinite as their mathematical counterparts?
Not really, no. Generally speaking, physicists are much more wary. Barrow explains that they tend to see physical infinities pop up in their equations as red flags.
Red flags.
Meaning signs that their current theories are incomplete, or that they've pushed those theories beyond the domain where they actually apply to reality.
It makes sense. In the tangible world, you rarely bump into something that is truly measurably infinite. Stuff usually has limits.
Precisely. Barrow gives some great examples of apparent physical infinities that turn out to have real-world resolutions.
Like what?
For instance, you might imagine the density of a gas becoming infinite if you squeezed it into an infinitely small space. But the reality is that molecules have a finite size, preventing that from happening. Or you might imagine infinite forces, but in the real world, things like friction and the fundamental limits of energy density step in.
And those funhouse mirrors.
Right. Even those parallel mirrors creating seemingly infinite reflections are ultimately limited by the imperfections of the mirrors. They don't reflect 100%, and crucially, the finite speed of light. The further images are dimmer and take longer to form.
So these apparent infinities are more like our idealized models, bumping up against the fuzziness and limitations of the real universe.
That's a good way to put it.
But what about in the really fundamental areas of physics, like elementary particles and cosmology? Surely infinity rears its head there.
Absolutely. In elementary particle physics, infinities popped up in calculations for decades, causing major headaches.
Infinite probabilities or energies.
Exactly. Physicists developed these clever mathematical techniques called renormalization to deal with them.
Renormalization. Sounds technical.
It is a bit. Think of it like subtracting an infinitely large, unobservable, bare quantity with another calculated infinity to get a finite, measurable result. A bit of a mathematical trick, perhaps, but it works incredibly well for making predictions that match experimental results.
So it works, but maybe it's sweeping something under the rug.
That's the debate. As Barrow points out, some physicists still see these infinities and the need for renormalization as a hint that we haven't yet reached the ultimate, most fundamental theory of everything.
And cosmology. Yeah, that's where you're talking about the universe itself, the Big Bang, the ultimate scales. Infinity must be a key player there.
Indeed. Cosmology throws up all sorts of potential infinite scenarios. There's the possibility of an infinitely large and eternally expanding universe stretching out forever in space and time.
The grandest scale imaginable.
Then you have the singularities. At the Big Bang, the universe's fiery origin, and the hypothetical Big Crunch, the opposite scenario, density and temperature are thought to have been infinitely high.
Infinite heat, infinite density.
Which leads to a breakdown of all our known physical laws. General relativity, quantum mechanics, they just stop working at a singularity. Barrow notes that Stephen Hawking, in particular, was deeply troubled by this idea of the fundamental rules of the universe just ceasing to apply.
It's like the ultimate game over screen for physics. And what about black holes? They're supposed to have singularities at their centers too, right?
Yes. The prevailing theory based on general relativity suggests that singularities with infinite density might form at the very heart of black holes, crushed down by their immense gravity.
So infinite density locked away inside.
Right. Barrow highlights the contrasting experiences. An observer outside a black hole's event horizon sees time essentially stop for anything falling in, while the theoretical experience of someone plunging into the black hole involves encountering that point of infinite density, a one-way trip.
Yikes. Finally, in this section, Barrow touches on transcendental absolute infinity. This sounds like we're venturing back into more philosophical territory.
It is. This is the concept of an ultimate, all-encompassing infinity, often associated with the idea of God or a supreme being. It's less a precise mathematical or physical concept.
More philosophical or mystical.
Exactly. It's about the totality of existence. Barrow briefly mentions ontological arguments for the existence of God that rely on this notion of a necessary infinite being as the ultimate ground of reality.
So from the tiniest particles to the vastest cosmos, and from the abstract world of math to the realm of belief, the idea of infinity keeps popping up, often presenting us with more questions than answers.
It certainly does.
Now, Barrow asks, infinity, where will it all end? This section seems to be focused on the universe itself. Is it finite or infinite?
This delves into the long-standing debate about the size and extent of the cosmos. Barrow credits Thomas Dix, a Renaissance scientist, as one of the early proponents of an infinite universe filled with stars.
Which was a radical departure from the earlier Aristotelian view of a finite, bounded universe.
Right. A massive shift in perspective, yeah. Imagining this boundless expanse stretching out without limit. But this idea of an infinite star-filled universe leads directly to the famous Olbers paradox.
Ah, yes. The perplexing question of why the night sky isn't blindingly bright.
Exactly. If the universe is truly infinite, static, unchanging, and filled with an endless number of stars distributed roughly uniformly, then no matter where you look in the night sky, your line of sight should eventually land on the surface of a star. The whole sky should appear as bright as the sun, day and night.
Which it clearly doesn't, so something's wrong with the assumptions.
Precisely. At least one of those assumptions must be incorrect.
And what are the modern resolutions to this paradox that Barrow discusses? Why isn't it daylight all the time, everywhere we look?
Several key factors come into play, mostly thanks to the Big Bang model. First, the universe has a finite age, about 13.8 billion years.
So light from the most distant stars hasn't had time to reach us yet.
Exactly. Our observable universe is finite in that sense. Also, the universe is expanding, and this expansion stretches the wavelengths of light from distant galaxies' redshift,
Making them dimmer and less energetic.
Right. And finally, while the universe is vast and contains a staggering number of stars, the average density of matter isn't infinite. There simply aren't enough stars packed closely enough to fill every single line of sight, even if the universe were spatially infinite.
So the darkness of the night sky isn't just dark. It's actually a clue, a piece of evidence pointing towards the Big Bang, the expansion, and the finite age of our universe.
It's a profound observation hidden in plain sight.
Barrow then touches on the geometry and topology of the universe and how that relates to the finite infinite question. This gets tricky.
It does. He explains how space itself could be finite without having a boundary or an edge.
Oh.
Think of the surface of a sphere like the Earth. You can travel around it endlessly in any direction without ever reaching a stop sign or falling off an edge.
Yet the total surface area is finite.
Exactly. Similarly, our three-dimensional space could be curved in on itself in a higher dimension, creating a finite total volume without needing a physical boundary. It could be shaped like a hypersphere, or even more complex shapes like a hypertorus, a 3D donut.
It's mind-bending to try and visualize a three-dimensional version of a sphere's surface. But the key takeaway is that finite doesn't automatically mean having a wall or a border.
Correct. And Barrow also makes that crucial distinction between the observable universe and the entire universe.
Remind us of that again.
The observable universe is the region from which light has had enough time to travel to us since the Big Bang. Because the speed of light is finite and the universe has a finite age, this region is also finite, currently about 93 billion light years across, actually, due to expansion.
Okay, that's our cosmic horizon.
But the entire universe could be much, much larger, possibly even spatially infinite, extending far beyond what we can currently, or maybe ever, see.
So we're essentially living in a cosmic bubble, limited by the speed of light. What's beyond the bubble, we just don't know for sure.
Precisely. Barrow then brings in the inflationary universe theory, which adds another layer of cosmic possibility.
Oh, inflation. That's super rapid expansion right after the Big Bang.
Yeah. Some versions of this theory, called eternal inflation, propose that this inflation might still be happening in incredibly distant regions, or perhaps it never stops everywhere. Different regions of space could undergo their own inflationary bursts.
Creating what?
Potentially creating an infinite number of bubble universes, each potentially vast or even infinite themselves, perhaps disconnected from ours, maybe even having different fundamental physical laws.
Different laws?
Yeah.
Like different gravity or particle masses?
Possibly. Different bylaws of this vast cosmic cosmopolis, as Barrow eloquently puts it.
Wow. So our entire universe, which feels unimaginably vast, might just be one tiny speck in this infinite foam of other universes, each with its own unique reality. That's a serious perspective shift.
It really is.
Okay, next up we have the infinite replication paradox. The name alone sends a shiver down my spine. What's the unsettling idea here?
It is unsettling. This paradox arises from the seemingly logical, if mind-boggling, conclusion that in an infinite universe, either infinite in space or existing for infinite time, or both, every single event that has even the tiniest non-zero probability of happening must occur. And not just once, but infinitely many times.
Wait, everything possible happens? Infinitely often. So somewhere out there, there's a version of me who decided to become a professional thumb wrestler.
If the universe is truly infinite and random quantum fluctuations allow for it, then yes, infinitely many versions of you who became professional thumb wrestlers and infinitely many who didn't.
Okay, this a lot.
Exactly. Barrow traces the philosophical roots of this idea back to thinkers like Nietzsche and Heine, who grappled with the concept of eternal recurrence.
Eternal recurrence.
If time stretches infinitely and the number of possible arrangements of matter and energy is finite, even if astronomically large, then every possible state of the universe must eventually repeat, infinitely often.
And the implications for us as individuals are what? Barrow mentions identical copies of ourselves living out every conceivable variation of our lives.
That's the core of the paradox. Somewhere in this infinite cosmos, or across infinite time, there would be countless identical copies of you with the same memories and thoughts up to a certain point, making slightly different choices, living out alternative versions of your life, every possible path taken.
Wow.
This raises profound questions about free will, individual identity, and the very significance of our actions. If every possibility is being played out an infinite number of times elsewhere, does this choice, this life, really matter?
It kind of diminishes that precious feeling of uniqueness, doesn't it? Like we're just one instance in an infinite cosmic rerun library.
It can feel that way. Barrow then brings in the literary works of Borges, like The Library of Babel and The Garden of Forking Paths, which explore similar themes.
Ah, Borges. Genius.
These are brilliant literary explorations of these mind-bending ideas. The Library of Babel, which contains every possible book composed of a certain alphabet and length.
Mostly gibberish, but also every great work ever written or to be written.
Exactly. And The Garden of Forking Paths depicts a universe where every choice creates a new branch of reality, leading to an infinite web of possibilities.
It's this overwhelming sense of infinite potential playing out in an infinite number of parallel narratives. But then Barrow offers a surprising counterpoint. Johnny Appleseed. Why bring this folksy figure into a discussion about infinite replication?
It's a great touch, I think. Johnny Appleseed, despite his widespread and lasting impact, was a single, finite individual. He performed a finite number of actions, planting a finite number of apple seeds, resulting in a measurable, finite, though widespread, positive effect. Barrow uses him as a grounding example.
To contrast the abstraction.
Exactly. To contrast the abstract, potentially paralyzing idea of infinite replicated actions with the concrete significance of a single, unique life making a tangible difference in the world. It's a reminder that even within the context of potentially infinite possibilities, our finite actions can still hold meaning and value.
That's a really insightful contrast. Despite the dizzying implications of infinite replication, our own limited lives and actions can still have genuine importance. That's comforting, actually.
I think so, too.
Now, Barrow moves on to infinite worlds, delving deeper into the fascinating realm of the multiverse.
This section explores the historical and modern perspectives on the possibility of multiple universes. Barrow recounts Aristotle's rejection of the idea.
He liked his finite, single universe.
Contrasting it with the atomist's view and Giordano Bruno's enthusiastic embrace of an infinite universe teeming with countless worlds. Bruno saw this as reflecting the infinite glory of God.
He got into a bit of trouble for that, didn't he?
A lot of trouble, unfortunately. It shows how radical the idea was.
And in contemporary cosmology, the idea of multiple universes has gained significant traction in various forms.
Right.
It's not just philosophy anymore.
Absolutely. Barrow discusses the fine-tuning problem of our universe. Why do the fundamental physical constants seem so perfectly dialed in for life?
Like the strength of gravity or the charge of an electron. Tiny changes would make stars or atoms impossible.
Exactly. One potential explanation is the multiverse. If there are an infinite or just very, very large number of universes, each with different physical constants generated randomly,
then it's not surprising we find ourselves in one where the conditions are just right for us to exist. We couldn't observe it otherwise.
Precisely. It's a form of the anthropic principle, sometimes called the life is easy argument within a multiverse context. Or maybe not easy, but just statistically inevitable somewhere.
Like winning a cosmic lottery with infinitely many tickets. Someone had to win, and the winners are the only ones who know there was a lottery.
That's a decent analogy. Barrow also delves back into the inflationary multiverse we touched on.
The eternal inflation idea.
Yes, the theory suggesting that different regions of space can undergo their own separate periods of rapid inflation, budding off to form independent bubble universes.
With potentially different physical laws.
Yeah.
The bylaws of the cosmopolis.
Right. It's an incredible image, an endless, ever-expanding network of universes, each a self-contained reality.
And then Barrow touches upon this even more out there idea of conscious interventions, almost like a cosmic version of the Men in Black intentionally creating baby universes.
Huh. Yeah, it's a more speculative concept, suggesting that highly advanced civilizations might be capable of engineering the creation of new mini-universes, perhaps in labs.
controlling the Big Bang on a small scale.
Maybe even influencing their fundamental properties. It raises profound questions about the potential role of intelligence in shaping the cosmos on the largest scales.
It's a kind of idea that blurs the line between science fiction and cutting-edge theoretical physics. Of course, no discussion of multiple realities is complete without considering the simulated universe hypothesis.
Ah, yes, the simulation argument, the intriguing, maybe unsettling notion that our reality might not be fundamental, but rather a sophisticated computer simulation run by some advanced civilization.
Are we living in the Matrix?
Sort of. Barrow discusses potential signs could we detect glitches. Would fundamental constants suddenly change if the simulators tweaked the code? He also touches on the deep ethical implications.
Yeah, what if they just turn us off?
Or, as Hume might suggest, what if our simulator isn't very good? He brings in Hume's skeptical perspective on a potentially flawed creation if multiple gods or simulators with varying levels of skill were involved.
It certainly makes you look at the world around you with a slightly more questioning gaze. Okay, moving on to relativistic supertasks. This sounds like physicists pushing the very limits of what's theoretically possible within Einstein's theory of relativity.
A supertask, as Barrow explains it, is the idea of accomplishing an infinite number of actions within a finite amount of time.
Infinite things in finite time. How?
Well, he begins with the classic Thomson's lamp paradox, a real philosophical brain teaser.
The lamp that gets switched on and off an infinite number of times. Remind me how that works.
You switch it on for, say, 30 seconds, then off for 15, then on for 7.5, off for 3.75, and so on. You keep having the time interval.
So the total time adds up to 1 minute, 30 plus 15 plus 7.5 plus...
Exactly.
Yeah.
You perform an infinite number of switches within that 1 minute period. The question, of course, is the lamp ultimately on or off at the exact end of that minute?
Oh, I have no idea. On, off, neither.
The paradox lies in the fact that there's no last switch. The state becomes logically indeterminate depending on how you try to sum up this infinite sequence. It highlights the weirdness that emerges.
It really does. Applying finite logic to an infinite process within a finite time. Tricky. Barrow also mentions the more general endgame problem.
Yeah, what would be the final state of any machine that could theoretically complete an infinite number of tasks? It's a profound conceptual challenge to the very idea of completing an infinite sequence. Can you even talk about the state after infinity?
He's problematic.
But then Barrow introduces the fascinating way that relativity throws a curveball into the supertask scenario.
How does Einstein's famous theory, with its time dilation and the relative nature of time, change the possibilities here?
Exactly. Relativity allows for situations where time passes differently for different observers. One observer moving at a very high speed relative to another can experience a finite amount of their own time, while witnessing what appears to be an infinite duration passing in the other observer's frame of reference due to extreme time dilation.
Like the twin paradox, where one twin travels fast and ages slower.
Precisely. The traveling twin experiences, say, 1 year, while the stay-at-home twin experiences potentially thousands or millions of years, depending on the speed.
So could a supertask be sort of possible from the perspective of someone experiencing time passing incredibly slowly relative to an outside observer? Like the outside observer sees infinite tasks completed in their finite time.
Barrow discusses work exploring this, like Itamar Petowski's idea of a hypothetical Platonist computer performing infinite computations along a specific space-time trajectory, while true supertasks performing infinite actions in their own finite time still present logical hurdles.
Right.
Relativity opens up these mind-bending possibilities where one observer could witness what seems like an infinite process unfolding within another's finite experience, or vice versa. He also briefly mentions Misner's Mixmaster universe, a theoretical model of the very early universe that undergoes an infinite number of oscillations as it approaches the initial singularity. Though quantum effects probably prevent that from being truly infinite in reality.
It's astonishing how the very fabric of space and time can warp and stretch in ways that allow for these seemingly paradoxical scenarios. Okay, we've reached the final chapter of this infinite journey, living forever.
A desire as old as humanity.
Yeah, indeed. Barrow explores the age-old human quest for immortality and delves into the various technological possibilities that have been proposed.
Things like advanced organ replacement, nanotechnology repairs, mind uploading into digital substrates, even cloning.
The prospect of extending human lifespan indefinitely through technology seems to be inching closer, maybe. But Barrow also thoughtfully examines the sociology of eternity. What kind of society would we end up with if people just stop dying?
Yeah, he raises some serious potential challenges. Overpopulation is the obvious one.
Infinite traffic jams.
But also the profound possibility of boredom. Would life lose its meaning without finitude? Would we value things less? And the complex legal and ethical issues imagine infinite prison sentences.
Yikes. It's not all sunshine and everlasting daisies in the land of forever, it seems. Barrow also brings in some weighty philosophical perspectives.
Referencing Unamuno's view that eternal life, as we might imagine it, could actually be terrifying.
A horrible immortality.
And Bernard Williams' exploration of the potential for infinite boredom and déjà vu, where eventually everything feels like a repeat.
They suggest that the very elements that give our finite lives, meaning urgency, change, growth, the preciousness of time, might be lost.
But Barrow also presents counter-arguments.
Reasons why immortality might not be boring.
Right. Pointing to the seemingly endless frontiers of intellectual exploration, think Gödel's incompleteness theorem suggesting math is inexhaustible, or the mysteries of prime numbers, plus artistic creation, human relationships, the boundless realms of imagination.
Maybe there's enough novelty in the universe, or that we could create, to keep things interesting forever.
Perhaps. It's an open question. And of course, no discussion about living forever in some form is complete without at least a nod to the tantalizing possibility of time travel.
Because if you live forever, why not visit the past or future?
Exactly. Barrow briefly touches on the theoretical possibilities, traversable wormholes, exploiting weird space-time geometries around rotating black holes or cosmic strings.
The stuff of sci-fi dreams.
But this immediately brings up the classic time travel paradoxes.
Like the grandfather paradox. What happens if you go back in time and prevent your own grandparents from meeting? Do you just vanish in a puff of logic?
Or the information paradox. Maybe you go back and give Shakespeare the idea for Hamlet. Where did Hamlet really come from, then?
Those self-referential loops that make your brain feel like it's trying to swallow itself. Barrow mentions the concept of consistent histories as a potential way out.
The idea, championed by physicists like Novikov, is that the laws of physics themselves might conspire to prevent paradoxes. Any attempt to create a contradiction would somehow fail.
So if you tried to shoot your grandfather, the gun would jam or you'd slip on a banana peel. The universe enforces consistency.
Something like that. Barrow uses a humorous example of a past injury preventing a time traveler from successfully carrying out a paradoxical act.
So the universe might have its own built-in self-preservation mechanism to protect the timeline. That's convenient.
It avoids the logical headaches, at least theoretically. Barrow also briefly mentions the tourists from the future problem.
Yeah, where are they? If time travel is possible, shouldn't we see them?
And the potentially overwhelming cumulative audience paradox if time travel became commonplace. Imagine infinite tourists piling up at the crucifixion or the moon landing.
Total chaos.
He also touches on the financial impossibilities of creating perpetual motion or perpetual money machines through time travel exploits, as these would violate fundamental principles like causality or conservation of energy.
No infinite money loops, darn.
And finally, he circles back to the Fermi paradox, where are all the aliens? Suggesting that maybe the inherent difficulties, dangers, or perhaps paradoxes associated with advanced technologies like time travel might be one reason why advanced civilizations don't spread everywhere or visit us.
Maybe reaching that level of tech is just too tricky or self-destructive.
It's one possibility among many.
So the dream of living forever and the allure of manipulating time are both incredibly complex and fraught with philosophical, sociological, and even logical challenges. It reminds us that even seemingly desirable infinities can come with some serious mind-bending caveats.
Absolutely. And the Infinite Book masterfully illustrates just how this concept, in its myriad forms, mathematical, physical, philosophical, continues to push the very boundaries of our understanding across a remarkable spectrum of human inquiry.
It really does. From the dizzying heights of Cantor's finite numbers, those different sizes of infinity,
mind-blowing,
to the unsettling depths of the infinite replication paradox. The idea of infinite copies of us.
Deeply weird.
And the truly mind-warping implications of relativistic supertasks, doing infinite things in finite time. It's clear that infinity is so much more than just a really, really big number.
It's a concept that fundamentally challenges how we think about everything.
Yeah.
Indeed. Barrow's work brilliantly highlights how grappling with the infinite forces us to confront the limits of our intuition and to reconsider our most basic assumptions about mathematics, physics, and the very nature of reality itself.
And now that you, our intrepid listener, have plunged into this deep dive with us, we have to ask, How has your own understanding of forever shifted?
What aspects of the infinite are still swirling around in that beautiful brain of yours? Did the hotel check you in or leave you scratching your head?
Huh?
We sincerely hope this exploration has ignited your curiosity and perhaps left you with a healthy dose of awe and wonder at the sheer strangeness and, well, beauty of the infinite.
Thanks for joining us on this mind-expanding journey into the boundless.
It's been fun.
Until our next deep dive, keep those big, maybe even infinite questions coming.